Hello everyone. Today we will study applications of recurrent relations. Recall. A recurrent relation for the sequence of an is the equation that express an in terms of one or more previous terms. In a sequence. A recurrent relation for sequence an is the equation that expresses an in terms of one or more previous terms in a sequence. Next, let's look at some examples about recurrent relation. First example. In a fish pond, there are initially there are initially 200 fishes. If the population of the fishes doubles every year, let A sub n represent the number of fishes in the fish pond. At the end of the nth year. Let an represent the number of fishes. Let an represent the number of fishes in the fish pond at the end of the nth years. Part A. Find a recurrent relation for an. Find a recurrent relation for an. So, for the recurrent relation, we try to write an in terms of the previous terms. Previous term is an minus 1. That's the previous term. For an, the previous term is an minus 1. What's the relationship between an and an minus 1? We know every year the population of the fishes doubles So population of this year is twice as many as last year. Population of fishes this year is twice as many as the population last year. And since the index must be greater than or equal to 0, in this formula, m must be greater than or equal to 1. Since the index must be positive, since the index must be non-negative, index cannot be negative here. So m must be greater or equal to 1. And since n starts from 1, we must consider A0 is a special case. We need to find A0 in a different way. Since for this equation, n starts from 1. So for A0, we consider A0 as a special case. A0 here represents the initial population. We know the initial population is 200. So here A0 is called the initial condition. This is called the recurrent relation. This is called the recurrent relation. We write an in terms of the previous terms. Part B. Use the recurrent relation to find the population of the fishes at the end of the 5 years. Use the recurrent relation to find the population of the fishes at the end of the 5th year. So we know A0 is 200. How do we find A1? For A1, we substitute 1 for n. So that's twice A1 minus 1 is 0. It's twice A0, which is 2 times 200, which is 400. A2, we substitute 2 for n. So 2 minus 1 is 1. That's twice of A sub 1. A sub 1 is 400. 2 times 400 is 800. For A3, we use 2 times A2. We substitute 3 for n. 3 minus 1 is 2. That's 2 times 800. It's 1600. For A4, we use 2 times A3. Plug in 4 for n. 4 minus 1 is 3. 2 times A3 is 2 times 1600, which is 3200. Then for A5, that represents the population of the fishes at the end of the 5 years. So A5 is 2 times A4. We substitute 4 for n. Substitute 5 for n. 5 minus 1 is 4. That's 2 times 3200. So the population of the fishes at the end of the 5 years is 6400. Part C. Find a closed form for an. A closed form for an means we write an without using the previous terms. A closed form for an means I write an without using the previous terms. So how do we find closed form for an? Let's start from the recurrent relation. The recurrent relation says a sub n equal to 2 times a sub n minus 1. Then how about a sub n minus 1? For a sub n minus 1, we plug in n minus 1 for n. If we plug in n minus 1 for n, I have twice am minus 2. Then how about a sub n minus 2? We plug in m minus 2 for n in the initial formula, in the initial recurrent relation. we plug in m minus 2 for n. We have twice an minus 3, and so on. Let's substitute. An is twice an minus 1. I can replace an minus 1 with twice an minus 2, which is 2 squared times an minus 2. Next, I can substitute. Replace an minus 2 with twice a sub n minus 3. So I replace an minus 2 with twice a sub n minus 3. If we simplify, we have 2 to the power 3 times a sub n minus 3. In general, you can see that the next term will be 2 to the power 4. If we substitute next term, it will be 2 to the power 4 times a n minus 4. In general, it will be 2 to the power n times a sub n minus n. 2 to the power 2, a sub n minus 2. 2 to the power 3, a sub n minus 3. 2 to the power 4, a sub n minus 4. In general, 2 to the power n times a sub n minus n. And a sub n minus n is a0. A sub n minus n is a0. A sub 0. The initial population, a sub 0 is 200. So substitute 200 here. An is 200 times 2 to the power n. This is a closed form for an. This is the closed form for an. We write an without using the previous terms. That's called a closed form for an. Part D. Use the closed form to find the population of the fishes at the end of the 5 years. So if we use this formula, a sub n represents population of the fishes at the end of the nth year. So we plug in 5 for the population at the end of the 5th year. We plug in 5 for n. We plug in 5 for n. A sub n represents population of the fishes at the end of the n years. So a sub 5 will be population of the fishes at the end of the 5th year. Plug in 5 for n. That's 200 times 2 to the power 5. 2 to the power 5 is 32. 200 times 32 is 6400. We get the same answer as part B. And using the closed form, we can get an answer in a much quicker way. Using the closed form, we can get an answer in a much quicker way. Next example. In the previous example, if the owner of the fish pond plan to catch and sell 180 fishes at the end of each year, let an represent the population of the fishes. And the end of the n year. In the previous problem, if an owner of a fish pond plans to catch and sell 180 fishes at the end of each year, the AN represents the population of the fishes at the end of the n years. Part A. Find a recurrent relation for AN. Find a recurrent relation for AN. A recurrent relation means I try to write AN in terms of the previous terms. How is the population this year and last year related? How do they related? How is the population of the fishes this year and the population of fishes in the previous year? How do they related? So we know every year, population of the fishes doubles its size. Every year, population of the fishes doubles its size. But the owner will catch and sell 180 fishes each year. So population will go down by 180. Every year, the population doubles. And the owner of the fish pond will sell 180 fishes. So the population goes down by 180 every year. And this is a recurrent relation. Based on this formula, n must be greater or equal to 1. Because the index cannot be negative. So n must be greater or equal to 1 because the index cannot be negative. Since here, n must be greater or equal to 1, we consider A0, A sub 0 is a special case. Since the index starts from 1, we consider A0 is a special case. A0 represents the population in the beginning. A0 represents the initial population, which is 200. Let's call recurrent relation. Part B. So, use the recurrent relation to find the population of the fishes at the end of the 5th year. Use the recurrent relation to find population of the fishes at the end of the 5th year. So let's compute A sub 5. Let's compute A sub 5. A sub 0 is 200. That's the initial population. For A sub 1, we substitute 1 for n. Substitute 1 for n. 1 minus 1 is 0. We have twice A sub 0 minus 180. A sub 0 is 200. Minus 180, that's 400 minus 180, which is 220. Now for A sub 2, we substitute 2 for n. Substitute 2 for n. 2 minus 1 is 1, so the index is 1. That's twice A1 minus 180. 2 times 220 is 440. 440 minus 180. That's 260. For A sub 3, we substitute 3 for n. That's 2 times A sub 3 minus 1 is 2. And A sub 2. That's twice A sub 2. 2 times 260 is 520. 520 minus 180 is 340. For a sub 4, we substitute 4 for n. That's 2 times a sub 3. 4 minus 1 is 3, so the index is 3 here. Minus 180. That's 2 times 340 minus 180. 2 times 340 is 680. 680 minus 180 is 500. What's a sub 5? A sub 5, we substitute 5 for n. It's twice a sub 4. 5 minus 1 is 4. Index is 4. Minus 180. A sub 4 is 500. 2 times 500 is 1,000. 1,000 minus 180 is 820. So the population of the fishes at the end of the 5th year is 820. Population of the fishes at the end of the 5th year is 820. That's how we calculate population. That's how we calculate AN using recurrent relations. So here you see that if we try to compute A5, we must compute A4 first. If we want to compute A4, we must compute A3 first. If we try to compute A3, we must compute A2 first. The computation for recurrent relation may take too much time. Next, let's try to find a closed form for AN. Next, let's try to find a closed form for AN. Part C. Find a closed form for AN. Find a closed form for AN means we write AN without using the previous terms. We try to write AN without using the previous terms. That's called closed form. So let's write down the formula first. AN is twice AN minus 1 minus 180. Let's write down a few more terms and try to see the pattern. For a sub n minus 1, I substitute a minus 1 for n. Substitute n minus 1 for n. We have a sub n minus 2. If I substitute n minus 1 here, m minus 1 is m minus 2. For an minus 2, we substitute m minus 1 for n. We have twice an minus 3 minus 180. For an minus 3, we substitute m minus 3 for n. We have twice a sub n minus 4 minus 180. Next, let's substitute and try to see the pattern. An is twice an minus 1 minus 180. If I substitute, I replace an minus 1 with the second row. Twice an minus 2 minus 180 minus 180. I substitute, replace an minus 1 with the second row. Twice an minus 2 minus 180. This 180 stays the same. Then if I simplify, I can distribute 2 into the parentheses. I have 2 squared an minus 2 minus twice 180 minus 180. Next, keep substitute. I replace an minus 2 with the third row. I have 2 to the power 2 2 to the power 2 stays the same. I replace an minus 2 with twice an minus 3 minus 180. The rest stays the same. Minus twice 180 minus 180. So I replace an minus 2. Replace a sub n minus 2 with the third row. The rest stays the same. Next, I can distribute 2 squared. If I distribute 2 squared, I have 2 to the power 3 a sub n minus 3 minus 2 squared times 180 minus 2 times 180 minus 180. Now, do you see the pattern here? Do you see the pattern here? we have 2 to the power 3 a sub n minus 3, 2 to the power 2, 180, 2, 180 minus 180. Can you estimate the next term? So next time, if I substitute a sub n minus 3, if I substitute a sub n minus 3 here, I will get 2 to the power 4, a sub n minus 4, minus 2 to the power 3, the power go down by 1. 2 to the power 3, 180, minus 2 square, 180, minus 2 times 180, minus 180. That's what I get if I replace a sub n minus 3 with the fourth row. Then, based on the pattern, if I keep substitute, I will have eventually get 2 to the power n, a sub n minus n, minus the power go down by 1, 2 sub n minus 1 times 180, minus 2 sub n minus 2 times 180. The power keep going down by 1. Eventually, it will reach 2 square times 180 minus 2 times 180 minus 180. That's what I get if I keep substituting the formula n times. Then the first term, a sub n minus n is a sub 0. For the rest, 180 is a common factor. For the rest of the terms, 180 is a common factor. I can pull out 180. If I pull out negative 180, I have 2 to the n minus 1 minus 2 to the power n minus 2. So it should be addition since I pull out negative 180. Plus 2 to the power 2 plus 2 plus 1. Then we know that a sub 0, the initial population is 200. A sub 0 is 200. So I get 200 times 2 to the power n minus 180 times this sequence. This is a geometry theory. This is a geometry theory. The sum for geometry theory is the next term 2 to the power n. The next term is 2 to the power n minus the first term over the common ratio minus 1. Common ratio here is 2. 1 times 2 is 2. 2 times 2 is 2 to the power 2. Common ratio is 2. So formula for geometry theory is the next term. Next term is 2 to the power n. The next term minus the first term over the common ratio minus 1. If we simplify this, 2 minus 1 is 1. We have 200 times 2 to the power n minus 180 times 2 to the power n minus 1. Because the denominator 2 minus 1 is 1. Then this should be 180. We have 180 times 2 to the power n plus 180, which is, if we combine like term, we have 20 times 2 to the power n plus 180. Part D. Using the closed form to find the population of the fishes at the end of the 5th year. Use a closed form to find population of the fishes at the end of the 5th years. The closed form is an equal to 20 times 2 to the power n plus 180. That's a closed form. An equal to 20 times 2 to the power n plus 180. That's a closed form. an equal to 20 times 2 to the power n plus 180. An represents population of the fishes at the end of the n years. For population of the fishes at the end of the 5th year, we substitute 5 for n. A sub 5 is 20 times 2 to the power 5 plus 180. 2 to the power 5 is 32. 20 times 32 is 640. 640 plus 180 is 820. So the population of the fishes at the end of the 5th year is 820, which is the same as what we get in part B. So here we can see that if we use the recurrent relation, for recurrent relation, it's easier to get a formula, but it's hard to compute. For recurrent relation, it's easier to get a formula, but it's hard to compute. But for the closed form, it's easier to compute, but it's hard to find a formula. It's easier to get an answer, but it's very hard to get a formula. Getting formula is not easy. For recurrent relation, getting the formula is easier, but it's hard to use the formula. For the closed form, it's easier to compute the answer, but it's hard to get a formula. Next example. Suppose you only have dollar bills, dollar coins, and $2 bills. And you want to make deposit. You want to make deposit to your bank account. Through an ATM machine. First question. In how many different ways can you deposit? In how many different ways can you deposit $n? In how many different ways can you deposit $n? Assume the order matters. Order matters means, suppose you want to deposit $3. If you deposit $2 first, then $1. And if you deposit $1 first, then $2. We consider there are different orders. We consider there are different ways. Order matters means if you deposit $2 first, then $1. Or if you deposit $1 first, then $2. We consider there are two different ways. That's what order matter means. In how many ways can you make deposit for $n? Of course, assume you have enough dollar bill, dollar coin, and $2 bills. Assume we have enough money to make deposit. In how many ways can you make deposit for $n? Assume the order matters. Let's set out the problem first. Let A sub n represent the number of ways, the number of different ways to deposit $n. Let A sub n represent number of different ways to deposit $n. So we know that the set of all possible ways to deposit $n that represent all possible orders to deposit $n. The first deposit, for the first deposit, there are three cases. For the first deposit, there are three cases. The first deposit could be either a dollar bill, dollar coin, or $2 bill. There are three cases. The first deposit is a dollar bill. Or the first deposit is a dollar coin. Or the first deposit is a $2 bill. For all possible orders, here A sub n represents all possible orders to deposit $n. For all possible orders, there are three cases. The first deposit is either a dollar bill, a dollar coin, or a $2 bill. There are three cases. The first deposit is either a dollar bill, dollar coin, or $2 bills. Look at case 1. Let's call this case 1. Let's call this case 2. Let's call this case 3. Case 1. If the first deposit is a dollar bill, then in order to complete the deposit, you need to make deposit for another $99. Sorry, for another M minus $1. Suppose the first deposit is a dollar bill. In order to complete the deposit of $n, you need to make a deposit for another M minus $1. And the number of ways to deposit M minus $1 is A sub M minus 1. The number of ways to deposit M minus $1 is A sub M minus 1. So similarly, for case 2, if the first deposit, for case 2, if the first deposit is a dollar coin, if the first deposit is dollar coin, then you need to make deposit for another M minus $1. If the first deposit is a dollar coin, then you need to make deposit for another M minus $1. The number of ways to make deposit for n-1 is a sub n-1. So the number of ways similarly the number of ways to deposit the remaining money is also n-1. If you make deposit for dollar coin, you have n-$1 left. In order to complete the deposit, you need to make deposit for n-$1. And the number of ways to deposit n-$1 is a sub n-1. Case 3. If the first deposit is a $2 bill, if the first deposit is a $2 bill, then the remaining money is n-2 dollars. You need to make deposit for another n-2 dollars. In order to complete the deposit, you need to make deposit for another n-2 dollars. The number of ways to deposit n-2 dollars is a sub n-2. So similarly, if the first deposit is $2, similarly, the number of ways to deposit the remaining money is n-2, because if you deposit $2, you still need to deposit n-2 more dollars. The number of ways to deposit n-2 dollars is a sub n-2. So all possible ways to make deposit of $n is a sub n. In the first case, if the first deposit is a dollar bill, if the first deposit is a dollar bill, the number of ways to complete deposit is a sub n-1. If the first deposit is a dollar coin, the number of ways to make deposit of $n is a sub n-1. If the first deposit is a $2 bill, the number of ways to make deposit for $n is a sub n-2. So therefore, we have a sub n equal to a sub n-1 plus a sub n-2 plus a sub n-2. A sub n-1 plus a sub n-1 plus a sub n-2. If the first deposit is a dollar bill, we have this many ways to complete the deposit of $n. If the first deposit is a dollar coin, we have this many ways to complete the deposit for $n. If the first deposit is a $2 bill, we have this many ways to complete the deposit for $n. Now, for this formula, since the index cannot be negative, so it only works when n is greater or equal to 2. Since the index cannot be negative, so n must be greater or equal to 2. Since we choose n to be greater or equal to 2 for this formula, then for n less than 2, we are considering their special cases. So we need to find a0 and a1 by itself. Those are special cases. Those are called initial value. Those are called initial value, initial condition. A sub 0. In how many ways can we make deposit for $0? In how many ways can we make deposit for $0? If there's no money to make deposit, there's only one way. This way means doing nothing. Doing nothing is considered one way. So the number of ways to make deposit for $0 is one way. This one way means doing nothing. we consider doing nothing is 1 way. And A sub 1 represents the number of ways to make departure for $1. The number of ways to make departure for $1, there are two choices. It could be either a dollar bill or dollar coin. So there are two ways to make departure for $1. There are two ways to make departure for $1. It could be either a dollar bill or dollar coin. So in general, this formula can be rewritten as A sub 0 equal to 1, A sub 1 equal to 2, AN equal to twice A sub n minus 1 plus AN minus 2 if n is greater or equal to 2. That's the recurrent relation. Part B. In how many different ways? Can you make deposit? For $7. In how many different ways can you make a deposit for $7? So for since A sub n represents the number of ways to make deposit for $n, so to find number of ways to make deposit for $7, we are looking for A sub 7. But since this is a recurrent relation, we must compute A0, A1, A2 up to A7. So let's list them out. Let's find everything out. A sub 0 is 1. A sub 1 is 2. A sub 2 represents the number of ways to make deposit for $2. The number of ways to make deposit for $2. Use the formula twice. If I substitute 2 for n, 2 minus 1 is 1, so index is 1 here. If I substitute 2 for n, 2 minus 2 is 0. We have A sub 0 here, which is twice A1 plus A0, which is 5. So there are 5 ways to make deposit for $2. How do we get 5 ways? It could be dollar bill, dollar coin, that's 1 way. It could be dollar bill, another dollar bill, dollar coin, dollar bill, or a dollar coin, another dollar coin, or we can make $2 bill directly. So there are 5 ways. To make deposit for $2. That makes sense here. How about A sub 3? Use the formula, we plug in 3 for n. That's twice A sub 2 plus A sub 1. A sub 2 is 5. A sub 1 is 2. 2 times 5 plus 2 is 12. A sub 4, we plug in 4 for n. We have twice A sub 3 plus A2. A sub 3 is 12. A sub 2 is 5. 2 times 12 is 24. 24 plus 4 is 29. A sub 5 is twice A4 plus A3. A4 is 29. A3 is 12. 2 times 29 is 58. 58 plus 12 is 70. A6 is twice A5 plus A4. A5 is 70. A4 is 29. 2 times 70 is 140. 140 plus 29 is 169. A7 is twice A6 plus A5, which is 2 times 169 plus 70. 2 times 169 is 338. 338 plus 70 is 408. So there are 408 ways to make deposit for $7. There are 408 ways to make deposit for $7. So for the current relation, we must compute A0, A1 up to A7. There's no shortcut. The way to find a closed formula for this equation is not easy. I'll show you next class. The way to find a closed formula, to find a closed form for this formula is not easy. I'll show you next class. Next. In the previous example, assume you only have $2 and $5 bills. In the previous example, assume you only have $2 and $5 bills. First question. In how many ways? In how many different ways? Can you make deposit? For N dollars. In how many different ways can you make deposit for N dollars? So let's set down a problem. Let AN represent the number of ways. The AN represents the number of different ways to deposit N dollars. The AN represents the number of different ways to deposit N dollars. Then the set of all possible ways to deposit N dollars. The set of all possible ways to deposit N dollars. That represents the number of all possible orders to deposit N dollars. For all possible orders, the first deposit could be either a $2 bill or $5 bill. The first deposit, there are two cases. The first deposit is either a $2 bill or the first deposit is a $5 bill. The number of all possible ways to deposit N dollars represents the number of all possible orders to deposit N dollars. So for all possible orders here, the first deposit could be either a $2 bill or a $5 bill. So there are two cases. In case 1, if the first deposit is a $2 bill, what's left, the remaining money, is M minus $2. The number of ways to deposit M minus $2 is the number of ways to deposit the remaining money is A sub M minus 2. If the first deposit is a $2 bill, what's left is M minus $2. We need to deposit M minus 2 more dollars. And the number of ways to deposit M minus $2 is A sub M minus 2. Case 2. If the first deposit is a $5 bills, if the first deposit is a $5 bill, the number of ways to deposit the remaining money is A sub m minus 5. If the first deposit is $5, we need to deposit m minus 5 more dollars because the total is n dollar. We need to deposit a total of n dollar. If the first deposit is $5, we need to deposit m minus 5 more dollars. And the number of ways to deposit m minus $5 is A sub m minus 5. So, therefore, all possible ways to deposit n dollar is A sub n. If the first deposit is $2, the number of ways to make deposit for n dollar is A sub m minus 2. If the first deposit is $5, the number of ways to make deposit for n dollar is A sub m minus 5 ways. So this is the current relation. Since the index cannot be negative, so here n must be greater or equal to 5. Since the index cannot be negative, so this m must be greater or equal to 5. If n is less than 5, what happens? If the amount is less than $5, if you want to make deposit for less than $5, then you cannot use your $5 bill. You can only use your $2 bill. So in this case, you can only make deposit for $2 bills. If you make deposit for $2 bills, what's the level is m minus $2. Then in order to make deposit for a total of n dollar, you need to make deposit for m minus $2. And the number of ways to make deposit for m minus $2 is A sub m minus 2. And here, since the index cannot be negative, this n here, for the second condition here, this m must be greater or equal to 2. Then for n less than 2, those are special cases. For n less than 2, you cannot make deposit for $1 or $0. For n less than 2, those are special cases. A sub 0. The number of ways to make deposit for $0 is one way, doing nothing. We consider doing nothing is one way. The number of ways to make deposit for $0 is one way. The number of ways to make deposit for $1. The number of ways to make deposit for $1 is no way. There's no way you can make deposit for $1 because you only have $2 and $5 bill. There's no way you can make deposit for $1. So number of ways to make deposit for $1 is 0. There are 0 ways you can make deposit for $1. So the recurrent relation, we write it over. The recurrent relation is A sub 0 equal to 1. A sub 1 equal to 0. An equal to A sub m minus 2. If n is between 2 and 5, equal to A sub m minus 2 plus A sub m minus 5. If n is greater than 5. So that's the recurrent relation. A sub 0 is 1. There's one way to make deposit for $0. There are no way to make deposit for $1. An is equal to A sub m minus 2 if n is between 2 and 5. A sub n equal to A sub m minus 2 plus A sub m minus 5 if n is greater than or equal to 5. That's the recurrent relation. part B. In how many different ways? Can you make deposit for $20? Since A sub n represents number of ways to make deposit for $n, so the number of ways to make deposit for $20 will be A sub 20. If we're looking for A sub 20, we need to use this formula here. This is a recurrent relation. If we try to find A sub 20, we must find A1, A2, A3 up to A sub 20. So let's compute everything here. A sub 0. Number of ways to make deposit for $0 is 1. 1 way, doing nothing. Number of ways to make deposit for $1 is impossible. That's 0. There are 0 ways to make deposit for $1. That's impossible. A sub 2. Here, 2 is between 2 and 5. We use this formula here. If I substitute 2 here, 2 minus 2 is 0. I have A sub 0. A sub 0 is 1. So A sub 2 is 1. There's 1 way to make deposit for $2. A sub 3. 3 is between 2 and 5. We use this formula here. It's if I plug in 3 here, 3 minus 2 is 1. That's A sub 1. And A sub 1 is 0. A sub 3 is 0, means there are 0 way to make deposit for $3. There are 0 way you can make deposit for $3. That's impossible. A sub 4. 4 is between 2 and 5. 4 is between 2 and 5. Substitute 4 here. 4 minus 2 is 2. I have A sub 2. A sub 2 is 1. So there are 1 way to make deposit for $4, which means $2 bills. A sub 5. 5 is greater or equal to 5. We use this formula here. Substitute 5. 5 minus 2 is 3. 5 minus 5 is 0. A sub 3 is 0. A sub 0 is 1. 1. That means there's only 1 way to make deposit for $5. There's only 1 way to make deposit for $5. A sub 6. 6 is greater than 5. We use the second formula. 6 minus 2 is 4. 6 minus 5 is 1. A sub 4 is 1. A sub 1 is 0, which is 1. There's a 1 way to make deposit for $6, which means 3 $2 bills. That's only 1 way. A sub 7, that's A sub 5 plus A sub 2. A sub 5 is 1. A sub 2 is also 1. 1 plus 1 is 2. There are 2 ways to make deposit for $7 bills. It could be either $5 bill first, $2 bill after, or $2 bill first, or $5 bill after. A sub 8, that's A sub 6 plus A sub 3, which is 1 plus 0, which means 1. There's only 1 way to deposit $8, which means 4 $2 bills. A sub 9, that's A sub 7 plus A sub 4. A sub 7 is 2. A sub 4 is 1. That's 3. A sub 10, that's A sub A plus A sub 5. A sub A is 1. A sub 5 is also 1. So there are 2 ways to deposit $10. It's either 2 $5 bill or 5 $2 bills. A sub 11. That's A sub 9 plus A sub 6. Plug in 11 for each n. A sub 9 is 3. A sub 6 is 1. 3 plus 1 is 4. A sub 12 is A sub 10 plus A sub 7. A sub 10 is 2. A sub 7 is also 2. 2 plus 2 is 4. A sub 13. Substitute 13 for n. We have A sub 11 plus A sub A. A sub 11 is 4. A sub A is 1. 4 plus 1 is 5. A sub 14 is A sub 12 plus A sub 9. A sub 12 is 4. A sub 9 is 3. 4 plus 3 is 7. A sub 15 is A sub 13 plus A sub 10. A sub 13 is 5. A sub 10 is 2. 5 plus 2 is 7. A sub 16. And that's A sub 14. We plug in 16 for each n. A sub 14 plus A sub 11. A sub 14 is 7. A sub 11 is 4. 7 plus 4 is 11. A sub 17 is A sub 15 plus A sub 12. A sub 15 is 7. A sub 12 is 4. 7 plus 4 is 11. A sub 15 is 7. A sub 12 is 4. 7 plus 4 is 11. A sub 18 is A sub 16 plus A sub 13. A sub 16 is 11. A sub 13 is 5. A sub 16 is 11. A sub 13 is 5. 11 plus 5 is 16. A sub 19 is A sub 17 plus A sub 14, which is A sub 17 is 11. A sub 14 is 7. A sub 17 is 11. A sub 14 is 7. 11 plus 7 is 18. So there are 18 ways to deposit $19. A sub 20 is A sub 18 plus A sub 15. A sub 18 is 16. A sub 15 is 7. 23. So there are 23 ways to deposit $20. There are 23 different ways to deposit $20 using only $2 and $5 bills, in which the order matters. Next example. In example number 3, assume you have only $2, $5, and $10 bills. In how many different ways? Can you make deposit of $20? In example 3, assume you have only $2, $5, and $10 bills. In how many different ways can you make deposit of $20? So it's very similar. Let's set out a problem first. The AN represent the number of ways to deposit the number of different ways to deposit n dollars. The AN represents the number of different ways to deposit n dollars. Since we are looking for number of ways to deposit $20, we are looking for A sub 20. We're looking for A sub 20. Let's first of all, let's find the recurrent relation first. Let's find the recurrent relation for AN first. So for AN represents the total number of different orders to deposit $20, to deposit n dollars. When you make first deposit, it could be either a $2 bill, $5 bill, or $10 bill. If you make $2 bill first, you have n minus $2 left. The number of ways to deposit n minus $2 is A sub n minus 2. Second case, if you make deposit for $5 first, if your first deposit is a $5 bill, if your first deposit is a $5 bill, you have n minus $5 left. The number of ways to deposit n minus $5 is A sub n minus 5. If you make deposit for $10, if you make your first deposit for $10, you need to deposit n minus 10 more dollars. And the number of ways to deposit n minus $10 is A sub n minus 10. That's the recurrent relation. And since the index must be positive, this formula works when n is greater or equal to 10. Since the index must be 0 or greater than 0, the index cannot be negative. Since the index must be 0 or positive, n must be greater or equal to 10. Now, if n is less than 10, you won't use $10 bills. If n is less than 10, you won't be able to use $10 bill to make a deposit. So you only use $2 or $5 bills. So you only make deposit for $2 or $8 as your first deposit. And in this formula, n must be greater than or equal to 5. In this formula, since the index cannot be negative, n must be greater than or equal to 5. And for n less than 5, if n is less than 5, if you're making deposit for fewer than $5, if n is less than 5, you only make deposit. You won't use $5. You won't use $5 bill to make deposit. So you won't use $5 bill to make deposit. You only use $2. You only use $2 bill to make deposit. AN is A sub n minus 2. If you make deposit for $2, you have n minus $2 left. The number of ways to deposit n minus $2 is A sub n minus 2. And this formula works when n is greater or equal to 2. Then, when n is less than 2, we consider there are special cases. A sub 0, the number of ways to deposit $0. The number of ways to deposit $0 is one way. Doing nothing is one way. Consider doing nothing is one way. A sub 1, the number of ways to deposit $1 is impossible. If you only have $2, $5, $10 bill, the number of ways to deposit $1 is impossible. It's 0. There are 0 ways you can make deposit for $1. So write the formula as A0 equal to 1, A1 equal to 0, AN equal to AM minus 2 plus AM minus 5 plus AM minus 10. If n is greater or equal to 10, AN equal to A sub n minus 2 plus A sub n minus 5. If n is between 10 and 5, including 5, and AN equal to AM minus 2. If n is between 2 and 5, including 2, then we can use the formula. Then we plug in. We try to find A sub 20. The number of ways to deposit $20 is A sub 20. So since this is a recurrent relation, We use this. We need to find A1, A2, A3 up to A sub 20. Find A1, A2, A3 up to A sub 20. That's the number of week. That's the number of week to deposit $20. So A sub 0 is 1. A sub 1 is 0. A sub 2. A sub 2, use this formula here. Since n is between 2 and 5, we use this formula. Substitute 2 here. 2 minus 2 is 0. That's A sub 0. A sub 0 is 1. Let me put the formula here. That's a little easier. A sub n is A sub n minus 2 plus A sub n minus 5 plus A sub n minus 10. If n is greater or equal to 10, A sub n minus 2 plus A sub n minus 5. If n is between 5 and 10, including 5 but not 10, A sub n minus 2 if n is between 2 and 5, including 2 but not 5. A0 is 1, A1 is 0. We are looking for A sub 20. We're looking for A sub 20, the number of weeks to deposit $20. A sub 3 is between 2 and 5. 3 minus 2 is 1. I get A sub 1, which is 0. A sub 4 is between 2 and 5. That's the same as A sub 2. A sub 2 is 1. A sub 5, or n is between 5 and 10, including 5. We use the second formula. That's A sub 3 plus A sub 0, plugging 5 here, plugging 5 for the index. A sub 3 is 0, A sub 0 is 1, which is 1. A sub 6 is A sub 4 plus A sub 1. A sub 4 is 1, A sub 1 is 0, which is 1. A sub 7 is between 5 and 10. We have A sub 5 plus A sub 2. A sub 5 is 1. A sub 2 is 1. 1 plus 1 is 2. A sub A. A is between 5 and 10. We have A sub 6 plus A sub 3. A sub 6 is 1. A sub 3 is 0, which is 1. A sub 9. 9 is between 5 and 10. Use this formula here. A sub 7 plus A sub 4. A sub 7 is 2. A sub 4 is 1. 2 plus 1 is 3. Then for A sub 10, A sub 10, 10 here is greater than or equal to 10. We use this formula here. For A sub 10, we plug in 10 for each n. We have A sub 8 plus A sub 5 plus A sub 0. A sub 8 is 1. A sub 5 is 1. A sub 0 is also 1. 1 plus 1 plus 1 is 3. A sub 11, use this formula. That's A sub 9 plus A sub 6 plus A sub 1. A sub 9 is 3. A sub 6 is 1. A sub 1 is 0, which is 4. A sub 12, plug in 12 here. We have A sub 10 plus A sub 7 plus A sub 2. A sub 10 is 3. A sub 7 is 2. A sub 2 is 1. That's 6. For A sub 13, we use A sub 11 plus A sub 8 plus A sub 3. A sub 11 is 4. A sub 8 is 1. A sub 3 is 0, which is 5. a sub 14, we have a sub 12 plus a sub 9 plus a sub 4. A sub 12 is 6. A sub 9 is 3. A sub 4 is 1, which is 10. For a sub 15, we have a sub 13 plus a sub 10 plus a sub 5. A sub 13 is 5. A sub 10 is 3. A sub 5 is 1. 5 plus 3 plus 1 is 9. For a sub 16, we use a sub 14 plus a sub 11 plus a sub 6. A sub 14 is 10. A sub 11 is 4. A sub 6 is 1. 11 plus 4 plus 1, that's 15. A sub 17 is a sub 15 plus a sub 12 plus a sub 7. A sub 15 is 9. A sub 12 is 6. A sub 7 is 2. 9 plus 6 plus 2 is 17. A sub 18 is a sub 16 plus a sub 13 plus a sub 8. A sub 16 is 15. A sub 13 is 5. A sub 8 is 1. That's 21. For a sub 19, that's a sub 17 plus a sub 14 plus a sub 9. A sub 17 is 17. A sub 14 is 10. A sub 9 is 3. Together is 30. A sub 20 is a sub 18 plus a sub 15 plus a sub 10. A sub 18 is 21. A sub 15 is 9. A sub 10 is 3. Together, that's 33. So there are 33 ways to deposit $20 if we only use $2, $5, and $10 bills. If we compare this solution with example number 4, we can see that if we have $10 bill, if we add $10 bill, there are more ways to make deposit. There are more ways to make deposit if we add more bills. If we add $10 bills, there are more ways to make deposit. This is example number 5. Compared to example number 4, we only use $2 and $5 bill. And if we add $10 bills, there are more ways to make deposit for $20. Next example, part A. How many bit strings of length n that do not contain a substring of 0, 0. A bit string is a string that only contains 0 and 1. A bit string is a string that contains only 0 and 1. That's called bit string. The question asks, how many bit string of length n that do not contain a substring of 0, 0? For example, 1001. This is a bit string. It contains a substring of 0, 0. Another example, 010100. That's a bit string. It contains a substring of 0, 0. 010101. This is a bit string. It does not contain a substring of 0, 0. This one contains a substring of 0, 0. This one contains a substring of 0, 0. And this one doesn't. This one does not contain a string of 0, 0. and we are looking for how many bit strings of length n that do not contain the substring of 0, 0. Let's set up first. Let's set up a problem first. Let a sub n represent the number of bit strings that do not contain a substring of 0, 0. Let an represent a number of bit strings that do not contain a substring of 0, 0. Here, an represents a number of bit strings that do not contain a substring of 0, 0. So let me write down an. An represents the number of bit strings of length n that do not contain 0, 0. That do not contain 0, 0. So this is an. The number of bit string of length n that do not contain 0, 0. How many different cases do we have for such string? How many different cases do we have? Let's look at the possible ending the string can have. Let's look at all possible two-digit ending first. For two-digit ending, the ending may be 1, 1, 0, 1, 1, 0, or 0, 0. For the ending, from the two-digit ending, all possible two-digit ending here is either 1, 1, 0, 1, 1, 0, or 0, 0. Those are all possible two-digit endings that a bit string can have. Now, in this case, since we're looking for bit string that do not contain a substring of 0, 0, so 0, 0 cannot be a possible ending. Since we are looking for bit strings that do not contain a substring of 0, 0, so 0, 0 cannot be a possible ending. This is all possible ending. Those are the possible ending that a string can have. In the first two cases, 1, 1 or 0, 1, the string actually ends with a 1. In the first two cases, 1, 1, 1 or 0, 1, the bit string ends with a 1. The bit string ends with a 1. In this case here, the string ends with 1, 0. In this case here, the string ends with 1, 0. The string ends with 1, 0, sorry, no comma, 1, 0. So there are two cases. The string either ends with a 1 or it ends with an n0. It won't end with 0, 0, since the string we're looking for do not contain a substring of 0, 0. So there are two cases. Case 1 is all such strings end with a 1. Case 1 is all such strings that ends with a 1. Plus the number of all such strings that ends with 1, 0. So those are two possible cases. If I add them up, I get a total number of bit string of length n that do not contain 0, 0. So those are two cases. Those are two possible cases. If I find a number for each set and add them up, I get an. Now, let's consider the first case. All such string ends with a 1. Let's consider a string of length n. And it ends with a 1. That's a string of length n. If a string with length n ends with a 1, then what's in the from? Is that's a string of length m minus 1. This is a bit string of length m minus 1. Since this string do not contain 0, 0, since the entire string do not contain 0, 0, then what we have here cannot contain 0, 0. Since the entire string do not contain 0, 0, then this string of length m minus 1 cannot contain 0, 0. So this is a bit string of length 1 that does not contain a substring of 0, 0. So this is a bit string of length m minus 1 that do not contain a substring of 0, 0. Since the entire string do not contain 0, 0, this substring here, it cannot contain 0, 0. How many strings are there? How many such strings are there? A sub n represents the number of bit strings that do not contain number of bit string of length n. Number of bit string of length n. A sub n represents the number of bit string of length n that do not contain a substring of 0, 0. So this is a bit string of length m minus 1 that do not contain a substring of 0, 0. So there are am minus 1 such strings. There are am minus 1 such strings. There are a sub m minus 1 such strings. So we have a sub m minus 1 such strings. If I add number 1 at the end, the number of strings stays the same. There are am minus 1 such strings of length m minus 1 that do not contain 0, 0. If I add 1 at the end, the number of strings stays the same. So there are a sub m minus 1 such strings ends with a 1. Plus the number of substring ends with 1, 0. How many such strings are there? Let's consider all such strings that ends with 1, 0. Let's consider all such strings of length n that ends with 1, 0. If a string ends with 1, 0, what's in the from? There are m minus 2 digits. If the string of length n ends with a 1, 0, then what's in the from? It's a string of length m minus 2. This is a bit string of length m minus 2. And since the entire string does not contain a substring of 0, 0, this string here, this string of m, this string in the from, it doesn't contain a substring of 0, 0. So this is a bit string of length m minus 2 that does not contain a substring of 0, 0. Since the entire string does not contain a substring of 0, 0, then this string in the from, it won't contain a substring of 0, 0. It won't be a 0, 0 here. And how many such strings are there? We know an represents the number of bit strings of length n that do not contain a substring of 0, 0. This is a bit string of length m minus 2 that do not contain a substring of 0, 0. So there are a sub m minus 2 such strings. There are a sub m minus 2 such strings here. Then for each string, if I add 1, 0 at the end, the number of strings stays the same. For each string here, if I add 1, 0 at the end, it won't generate a substring of 0, 0, and the number of substrings stays the same. If I add 1, 0 at the end, it won't generate 0, 0. So the number of strings stays the same. If I add 1, 0 at the end, number of strings stays the same. There are a sub m minus 2 such strings. So number of such string that ends with 1, 0 is a sub m minus 2. So here we can see that an equal to a sub m minus 1 plus a sub m minus 2. This is the recurrent relation for an. Where an represents a number of bit string of length n that do not contain a substring of 0, 0. And for this recurrent relation, since the index cannot be negative, so this formula works if n is greater or equal to 2. This formula works if n is greater or equal to 2 because the index cannot be 0. The index cannot be negative. Index may be 0, but it cannot be negative. So m must be greater or equal to 2. Now, this formula works for n is greater or equal to 2. So we consider a sub 0 and a sub 1 as special cases. Those are the initial conditions. What's a sub 0? A sub 0 represents the number of bit string of length 0. The number of bit string of length 0 that do not contain 0, 0. The number of bit string of length 0 is an MP string. The number of bit strings of length 0 is an MP string. So we consider as one of them. MP string is one of the strings. We consider an MP string is also one of the strings. So there's only one string, the MP string. The MP string guarantees it won't contain 0, 0. MP string guarantees it won't contain 0, 0. A1 is the number of bit string of length 1. A1 represents the number of bit string of length 1 that do not contain 0, 0. Bit string of length 1 contains only one digit. It guarantees it won't have a 0, 0. Bit string has only one digit. It won't contain 0, 0. Bit string of length 1. This contains only one digit. One digit won't have 0, 0. So a bit string of length 1 could be either the string of 0 or the string of 1. So there's only two possibilities. There's the number of bit string of length 1. It could be either the string of 0 or the string of 1. There's only two possibilities. Those are the initial conditions. So The recurrent relation can be written as A0 equal to 1, A1 equal to 2, AN equal to A sub n minus 1 plus A sub n minus 2 if n is greater or equal to 2. That's the recurrent relation. That's the recurrent relation for AN. Now part B. Number 6, part B. How many bit strings of length 5? How many bit strings of length 5 that do not contain a substring of 0, 0. How many bit strings of length 5 that do not contain substring of 0, 0? So based on this definition here, AN represents the number of bit strings of length n do not contain a substring of 0, 0. We are actually looking for A sub 5. We are looking for A sub 5. And since this is a recurrent relation, if we try to compute A5, we must compute A0, A1, A2, A3 up to A5. So let me put a formula here. A0 is 1, A1 is 2, AN is AN minus 1 plus AN minus 2 if n is greater or equal to 2. So A0 is 1, A1 is 2, A2, we plug in 2 for each n. When n is greater or equal to 2, plug in 2 for each n. We have A sub 2 minus 1 is 1, 2 minus 2 is 0, A1 plus A0 is 2 plus 1 equal to 3, A3, we plug in 3 for n. We have 3 minus 2 is 1, 3 minus 1 is 2, 3 minus 2 is 1, A2 is 3, A1 is 2, I get 5. A4 is A3 plus A2, which is 5 plus 3. Which is 8. A5 is A4 plus A3, which is 8 plus 5, which is 13. So there are 13 bit strings of length 5 that do not contain a substring of 0, 0. Next example. Let's consider all decimal strings. A decimal string is a string formed by digits. Digits means number from 0 to 9. Decimal string is a string formed by digits. Digits means the numbers from 0 to 9. Let AN represent the number of decimal strings of length n that do not contain a substring of 0, 0. The AN represents a number of decimal string of length n that do not contain a string of 0, 0. First question. Find the recurrent relation for an. Find the recurrent relation for an. Here, an represents the number of decimal strings of length n that do not contain 0, 0. an represents the number of decimal strings of length n that do not contain a substring of 0, 0. This is an. This is a sub n. Let's look at different cases. How many different endings can we have? How many possible endings can we have? Decimal strings. Let's consider all possible two-digit endings first. Let's consider all possible two-digit endings first. The ending may be 0, 0. Maybe a 0 with a non-zero number. Or it may be both non-zero number. It may be both non-zero number, or it may be a non-zero number, then a zero number. Those are all possible endings. It could be both zeros, could be 0 or non-zero, 0 followed by a non-zero number, or both non-zero number, or a non-zero number followed by a 0, where x equal to 1, 2, 3, up to 9. X cannot be 0. S is a non-zero number. Here, SX doesn't mean they are the same. It could be 2, 3, 4, 7, 1, 9. XS represent a decimal number. They may not be the same. They may be different decimal numbers. They may be different decimal number. It could be, S represent a non-zero decimal number. It could be X represent a non-zero digit. It could be different digits. This S could be different digits. It doesn't mean they are the same digit. It could be different digits. It could be 1 here, 2 here, 7 here, 9 here. X represent a non-zero digit. So, since the string do not contain a substring of 0, 0, the two-digit ending cannot be 0, 0. The two-digit ending cannot be 0, 0. So those are the possible two-digit ending. It cannot be 0, 0. It could be a 0 followed by a non-zero number, or a non-zero number followed by a non-zero number, or a non-zero number followed by a 0. In these two cases, the ending is always a non-zero number. In these two cases, the last digit it ends with a non-zero digit. For these two cases, it ends with a non-zero digit. The string ends with a non-zero digit. In this case, the string ends with a non-zero digit followed by a 0. The string ends with a non-zero digit followed by a 0. So those are two possible outcomes. Those are two possible endings. Those are two possible endings of the string. Those are two possible endings of the string. So there are two cases. For all such string, it may end with a non-zero digit, or it ends with a non-zero digit followed by a 0. So there are two cases. This number is the same as the number of all such strings that ends with x, where x cannot be 0, x equal to 1, 2, 3 up to 9. Or it could be the number of all such strings. It could be all such strings that ends with x 0, where x equal to 1, 2, 3 up to 9, x cannot be 0. So for all such numbers, for all such strings, there are two cases. It could be all such string ends with a non-zero digit, or all such string ends with a non-zero digit followed by a 0. Together it's an. Together it's an. There are two different cases. If I add them up, I get an. Now let's try to find the number of each set individually. Let's try to find the number of each set individually. First case, we have a string of length a. A string of length n ends with x. A string of length n ends with x, where x could be 1, 2, 3, 4, 5 up to 9. That's a string of length n ends with x. That's case 1. A string of length n ends with x. And this string do not contain 0, 0. This string do not contain 0, 0. If the last digit is n, what's in the front? What's in the front? This is a string of m minus 1. This is a string of length m minus 1. This is a decimal string of length m minus 1. This is a decimal string of length m minus 1. And it doesn't contain a substring of 0, 0. This is a decimal string of length m minus 1, and it doesn't contain a substring of 0, 0 because the entire string does not contain 0, 0. So a substring here won't contain 0, 0. And how many such strings are there? We know that an represents the number of decimal strings of length n that do not contain a substring of 0, 0. So since this string that does not contain 0, 0, we have a sub m minus 1 such strings. And we know that there are a sub m minus 1 such strings, because an represents the number of decimal string of length n that do not contain substring of 0, 0. This is a decimal string of length m minus 1, and it does not contain a substring of 0, 0. So we know that there are a sub m minus 1 such strings. And for each string, if I add a non-zero number to the end, the number of strings stays the same. For each string here, if I add a non-zero number to the end, it won't generate 0, 0. If I add a non-zero number to the end, if there's no 0, 0 here, if I add a non-zero number to the end, it won't generate 0, 0. So the number of string of length n stays the same. So there are a m minus 1 such strings. But here, since x could be 1, 2, 3, 4, 5, up to 9, when x equal to 1, we have this many strings. When x equal to 2, we also have this many strings. When x equal to 3, 4, 5, up to 9, we have this many strings. So since we have 9 choice for x, we have a sub n minus 1 choice for this string here. We have 9 choice for x. By counting principle, we multiply this number out. We have 9 times a sub m minus 1 such strings. We have a total of 9 times a sub m minus 1 such strings. So there are a sub m minus 1 such string in the front, and we have 9 choice for x. So the total number of strings, take a sub m minus 1 times 9. So if we have 9 times a sub m minus 1 such strings. Second case, if the string ends with a non-zero number followed by a 0. Case 2, a string of length n ends with a non-zero number followed by a 0. A string of length n followed by a non-zero number followed by a 0. And x could be 1, 2, 3, 4, 5, up to 9. There are 9 choice for x. X could be 1, 2, 3, 4, 5, up to 9. There are 9 choice for x. How many? Since there are 2 digits at the end, what's in the front here? This is a decimal string of length n minus 2. This is a decimal string of length m minus 2. The total is n. The last 2 digits is x followed by a 0. So we have m minus 2 digit here. This is a decimal string of length m minus 2. Since the entire string does not contain 0, 0. A substring here won't contain 0, 0. And it does not contain a substring of 0, 0. This is a decimal string of length n sub m minus 2, and it does not contain a substring of 0, 0. How many such strings are there? We know an represents a number of decimal string of length n that do not contain a substring of 0, 0. This is a substring of length m minus 2 with the same property. So there are a sub m minus 2 such strings. And since here we have a sub m minus 2 choice for this string here, we have a sub m minus 2 strings for this substring here. And then x has 9 choice. X could be 1, 2, 3, 4, 5, up to 9. So we have 9 choice for x. We have a sub m minus 2 choice for this substring. We have 9 choice for x. When I add x0, it won't generate 0, 0. When I add x0 here, it won't generate 0, 0. So the number of string of length n is the same as the number of string of length m minus 2. And since we have a sub m minus 2 choice for this substring, we have 9 choice for x. So together we have 9 times a sub m minus 2 choice for this substring. So together we have 9 times a sub m minus 2 choice for this string. So we have the recurrent relation is a sub n equal to 9 times a sub n minus 1 plus 9 times a sub n minus 2. So this formula only works if n is greater or equal to 2, because the index cannot be negative. Then we consider a sub 0, a sub 1 as special cases. A sub 0, if a string has length 0, it's an NP string. NP string guarantees it won't contain 0, 0. So we have only one choice. We have one choice here. We have one such string, the NP string. We have one such string, the NP string. NP string is a string that do not contain 0, 0. A1, A sub 1. A sub 1 represents a string of length 1. A sub 1 represents a string of 1 that do not contain 0, 0. A string have length 1 guarantees it won't have 0, 0. String of 1 could be either string of length 1 could be either 0, 1, 2, 3, 4, 5 up to 9. So there are 10 such strings. So if I write the recurrent relation, I have A0 equal to 1, A1 equal to 0. Those are called the initial condition. The recurrent relation is A sub n equal to 9 times A sub n minus 1 plus 9 times A sub n minus 2. Let me put the formula here. Part B. How many decimal strings of length 5 that do not contain a substring of 0, 0? How many decimal strings of length 5 that do not contain a substring of 0, 0? So since A sub n represents number of decimal strings of length n that do not contain 0, 0, we're looking for decimal strings of length 5 that do not contain a substring of 0, 0. We're actually looking for A sub 5. This is the recurrent relation. We must compute A sub 0, A sub 1, A sub 2, up to A sub 5. There's no shortcut. A sub 0 is 1. A sub 1 is 10. A sub 2 is 9 times A n is 2. N is 2, which is 9 times 10 plus 9 times 1. 9 times 10 is 90. 9 times 1 is 9. So we have 99. There are 99 strings. There are 99 decimal strings of length 2 that do not contain 0, 0. A sub 3 will be 9 times A2 plus 9 times A1. It's 9 times 99 plus 9 times 10. In my calculator, I get 981. For A4, we have 9 times A3 plus 9 times A2. That's 9 times 981 plus 9 times 99. In my calculator, I get 9720. Next, for A5, 9 times A4 plus 9 times A3. I have 9 times 9720 plus 9 times 981. In my calculator, I get 96,309. 96,309. We have this many decimal strings of length 5 that do not contain the substring of 00, 0. Next example. Consider all decimal strings. Let A sub n represent the number of decimal strings of length n that contain a substring of 00. Let AN represent number of decimal strings of length n that contains a substring of 00. First question. Find a recurrent relation for AN. Find a recurrent relation for AN. So AN represents the number of decimal strings of length n that contains 00. That contains 00. So AN represents number of decimal string of length n that contains 00. Let's calculate AN by cases. How many different cases do we have? This is AN. Let's calculate AN by cases. How many cases do we have? Again, let's consider its possible two-digit ending. Its 00 has 2 digits. Let's consider its possible two-digit ending. Let's consider its possible two-digit ending. It may end with 20. It may end with a 0 and with a non-zero number x. It may end with both non-zero number x, or it may end with a non-zero number x, then a 0. There are 4 different cases. So here, since it contains a substring of 00, now since it contains a substring of 00, since AN represents number of decimal string that contains 00, we must include all 4 cases. So in this case, the last digit is non-zero. We can combine these 2 cases together. The last digit is 0. The last digit is non-zero. Here x cannot be 0. And each x may not be the same. Each x may not be the same. X represents non-zero digits. And each x may not be the same. For example, Sx here may be 3 and 5, maybe 7 and 9, maybe 8 and 2. Each x may represent different numbers. In these 2 cases, it ends with a non-zero digit. in these two cases, the string ends with a non-zero digit. The string ends with a non-zero digit in this case. Now, for these two cases, we cannot consider them together. For these two cases, we cannot consider this as one case, because in the first case, we have 0, 0 at the end. In the second case, in the last case, since if we contain 0, 0, if the string contains 0, 0, we must have 0 in the middle. In the first case, we have 0 at the end. We have 2 zeros at the end. In the last case, if the string contains 2 zeros, we may have 2 zeros in the middle, and we don't have 2 zeros at the end. So they are two different cases. We cannot consider these two cases together, because in the first case, we have 2, 0, 0, we have 0 zeros at the end. In the last case, we have 0 zeros in the middle. So we cannot consider this as one case. We must consider this as two different cases. In this case, the string ends with a non-zero digit followed by a 0. In this case, the string ends with a non-zero digit followed by a 0. In this case, the string ends with 2 zeros. The string ends with 2 zeros. So let's consider these three cases individually. So the string may end with 2 zeros. The number of all such strings that ends with two zeros. That's the first case. It could be all such strings end with 2 zeros, plus all such strings end with a non-zero digit. The number of all such strings that end with x, where x cannot be 0, x equal to 1, 2, 3 up to 9. That's the second case. The third case, it could be all such strings that end with x0. The number of all such strings that end with x0, where x equal to 1, 2, 3, 4, 5 up to 9. So there are three different cases. Let's compute the number of each set individually. Let's compute the cardinality of each set individually. This is a new case. Let's do this case later. Let's consider all cases first. This is a new case. Let's do this new case later. Consider all cases first. For the second case here, the number all such string ends with a x, where x is 1, 2, 1, 2, 3, 4, 5 up to 9. So we have a string of length n. Let end with x. A string of length n. Let end with x. S could be 1, 2, 3 up to 9. So if this string contains 2 zeros, this represents all string contains 2 zeros. If the entire string contains 2 zeros, and the last digit is not 0, we must have 2 zeros in the middle. If this string contains 2 zeros, this is one of the string that contains 2 zeros. If the entire string contains 2 zeros in the middle, and the last digit is not 0, it must have 2 zeros in the middle. So this is a string This is a decimal string of length m minus 1. This is a decimal string of length m minus 1. That contains a substring of 200. If the entire string contains 2 zeros and the last digit is not 0, it must have 0 somewhere in the middle. So this is a decimal string of length m minus 1 that contains a substring of 00. Can we tell how many such strings are there? How many such strings are there? We know that a sub n represents the number of decimal string of length n that contains a substring of 00. So this is a decimal string of length m minus 1 that contains a substring of 00. This length is m minus 1. So there are a sub m minus 1 such strings. There are a sub m minus 1 such strings here. We have a sub m minus 1 choice for this string here. And since we have 9 choice for x, no matter what the last digit is, if I add a number from 1 through 9 here, it won't generate 00. It won't generate 00. So we have a sub m minus 1 choice here and 9 choice here. Totally, we have 9 times a sub m minus 1 such strings. We have 9 times a sub m minus 1 such strings that ends with x. Next, let's consider all such strings end with x0, where x is from 0 to 9. X is from 1 to 9. Let's consider a string of length n that ends with x0, where x represents numbers from 1 to 9. X represents numbers from 1 to 9. If this string has length n, if this string has length n, and it contains 2 zeros. If this string has length n, it contains 2 zeros. This 2 zero cannot be here, so it must be somewhere in the middle. So this is a decimal string of length m minus 2. The total length is n. And there are 2 digits here. This string must have the length m minus 2. This is a decimal string of length m minus 2 that contains a substring of 00. since the entire string contains 0, 0, since the entire string contains 0, 0, 0, 0 is not here. It must be somewhere in the middle. And can we tell how many such strings are? Can we tell how many such strings are there? We know AN represents the number of decimal strings of length n that contains substring 0, 0. This is a decimal string. This is a decimal string of length m minus 2 that contains a substring of 0, 0. So we know that there are a sub m minus 2 such strings. And how many choices do you have here? We have a sub m minus 2 choice here. And since we have 9 choices for x, we have 9 choices for the last 2 digits. So since we have a sub m minus 2 choice for this substring, we have 9 choices for xo. Together we have 9 times a sub m minus 2 choice for this string. So there are this many strings here. The third case, that's the new case here. The number of all such strings ends with 2 zeros. How many such strings are there? Strings end with 2 zeros. Strings end with 2 zeros. How many such strings are there? That's a newer case. A string that ends with 2 zeros. Of length n. That's a string that ends with 2 zeros of length n. In this situation, if the string ends with 2 zeros, it guarantees the string will have a substring of 0, 0. In the third case, this string guarantees it has 2 zeros. It has 2 zeros together. No matter what I put here, no matter what right here, it guarantees it always have a substring of 0, 0. So this number here could be arbitrary, it could be any number. So we have 10 choice for this digit, 10 choice for this digit, 10 choice for all these digits. Together we have 10 to the power m minus 2. We have this many digits. That ends with 2 zeros. We have this many digits that contains 2 0, 0, that contains 0, 0. That's the third case. That's the first case here. If a string ends with 2 zeros, no matter what I put here, no matter what I put in the front, it guarantees the string has a consecutive zeros. In this case, no matter what I put in the front, it guarantees a substring of 0, 0. No matter what I put in the front, it guarantees a substring of 0, 0. So this number could be any number. There are 10 choices for each digit. So, and we have m minus 2. We have m minus 2 digits here. Since there are 2 digits here, we have m minus 2 digits here. Each digit has 10 choices. So we have 10 to the power of m minus 2. No matter what I put here, it guarantees a substring of 0, 0. So the recurrent relation here is a sub n equal to 10 to the power m minus 2 plus 9 times a sub m minus 1 plus 9 times a sub m minus 2. Then this formula only works for, since the index cannot be negative, this formula only works if n is greater or equal to 2. This formula only works when n is greater or equal to 2. If n is less than 2, we have a0 and a1. Those are special cases. We need to solve it in a different way. For a0 and a1, those are special cases. We have to find it in a different way. a0 represents a string of length 0. If n is 0, we have a string of length 0. A string of length 0 is an MP string. MP string won't contain 0, 0. MP string won't contain 0, 0. So there are 0 string of length 0. There are 0 string of length 0 contains 0, 0. There are 0 such strings contains 0, 0. Because the MP string doesn't contain 0, 0. So no such strings. If the length is 0, there are no such strings. Or if the length is 1, length is 1 is a single digit string. A single digit string won't contain 0, 0. It won't have a substring of 0, 0. So that's also impossible. 0, 1, these strings do not contain 0, 0. So there are no such string. No string of length 1 contains a substring of 0, 0. So the current relation here can be written as A0 equal to 0, A1 equal to 0. Those are the initial conditions. A sub n equal to 10 to the power of n minus 2 plus 9 times A sub n minus 1 plus 9 times A sub n minus 2 if n is greater or equal to 2. Part B. How many decimal strings? Of length 5. That contain a substring of 0, 0. How many decimal strings of length 5 that contains a substring of 0, 0? So let me put a formula here. A sub 0 is 0. A sub 1 is 0. A sub n is 10 to the power n minus 2 plus 9 times A sub n minus 1 plus 9 times A sub n minus 2 if n is greater or equal to 2. And since this is a current relation, if we try to compute A5, we must compute each one individually, A0, A1, A2, up to A5. This AN represents number of decimal strings that contains a substring of 0, 0. AN represents number of decimal string of length n that contains a substring of 0, 0. We are looking for a decimal string of length 5 that contains a substring of 0, 0. That means we are looking for A sub 5. This is a current relation. We must compute each one individually from A0, A2, A3 up to A5. A0, that's 0. A1 is also 0. A2, when n is greater or equal to 2, use the formula. Plug in 2 for each n. 2 minus 2 is 0. 2 minus 1 is 1. 2 minus 2 is 0. So 10 to the power 0 is 1. 9 times 0 is 0. 9 times 0 is 0, which is 1. That means there's only one string of length 2 that contains a substring of 0, 0, which is 0, 0 itself. A sub 3, we substitute 3 for each n. That's 10 to the power 1 plus 9 times A sub 2 plus 9 times A sub 1. 10 to the power 1 is 10. 9 times A2 is 9. A2 is 1. 9 times A1 is 0, which is 19. So we have 19 such strings. A sub 4, substitute 4 for each n. I get 10 squared plus 9a to the power 3 plus 9a squared. 10 squared is 100. 9 times a3 is 19. 9 times a2 is 1. I use my calculator, I get 280. Next, A5, A sub 5 is plug in 5 for each n. We have 10 to the power 3 plus 9 times a sub 4 plus 9 times a sub 3. 10 to the power 3 is 1000. A sub 4 is 280 plus 9 times 18. Again, I use my calculator. I get 3691. So we have this many decimal strings of length 5 that contains a substring of 0, 0. Next, let me introduce a very, very famous problem. In an island, a pair of rabbits do not breathe. A pair of rabbits do not breed. A pair of rabbits does not breed until they are 2 months old. A pair of rabbits does not breed until they are 2 months old. After they are 2 months old, each pair of rabbits produce another pair. Of rabbits. Each month. So a pair of rabbits does not breed until they are 2 months old. After they are 2 months old, each pair of rabbits produce another pair of rabbits each month. Assume there is only one pair of newborn rabbit. Assume there's only one pair of newborn rabbits in the island. In the first month. Assume there's only one pair of newborn rabbits in the island in the first month. And the rabbits never die. Let f sub n represent the number of rabbits in the island. In the n months. Let f sub n represent number of rabbits in the island in the n months. First question. Find a recurrent relation for Fn. Find the current relation for Fn. So F sub n represents the number of rabbits in the island in the nth month. How can we find the current relation for F sub n? F sub n represents the number of rabbits in the nth month. So since every month the rabbit produce another pair. Every month all rabbits produce another pair of rabbits. So the population in the nth month has two parts. It has newborn rabbits and existing plus existing rabbits. The population of rabbit in the nth month has two parts: newborn rabbits plus existing rabbits. And same thing in the previous month. In the previous month, it only contains two parts. Newborn rabbits plus existing rabbits. That's the population of the rabbit in the island. That's the rabbit in the previous month. And look at the nth month. Existing rabbit is the number of rabbit from the previous month. The existing rabbit in the nth month is the number of rabbit in the previous month. It doesn't matter if it's newborn or existing. The existing rabbit in the nth month is the number of rabbit in the previous month. All rabbit in the previous month become existing rabbit in the nth month. So this is the same as f of m minus 1. How do we calculate the number of newborn rabbits? How do we calculate the number of newborn rabbits? Look at the previous month. Previous month, the number of rabbits is f of m minus 2. And all rabbit become existing rabbit. All rabbit here become existing rabbit in the month of m minus 1. All rabbit here become existing rabbit in the month of m minus 1. Now, this existing rabbit in the month of n, this is n minus 2 months. This is m minus 2 months. This is m minus 1 month. This is the nth month. All rabbit here, all rabbit exists here. All rabbit exists in the month of m minus 2 months. All this rabbit here, in the nth month, they are at least 2 months old. All existing rabbit in the month of m minus 2. All existing rabbit in the month of m minus 2 become at least 2 months old in the nth month. So this rabbit here become existing rabbit in the n minus 1 month. And all this rabbit here will be at least 2 months old. All this rabbit here will be at least 2 months old in the nth month. So they can produce a new pair of rabbits. So all existing rabbit here in the nth month will be at least 2 months old. So they can produce new babies. They can produce new rabbits, new pair of rabbits. So this number is f of m minus 2. This number, since each pair produce one pair, since each pair of rabbit produce another pair of rabbit. So the number of newborn pair is the same number of existing pair in the previous month. So f sub n is f sub m minus 2 plus f sub m minus 1. usually write f sub n minus 1 first. F sub n minus 1 plus f sub n minus 2. Again, since the index cannot be negative, m must be greater or equal to 2. Since the index cannot be negative, n must be greater or equal to 2. For n less than 2, we need to consider this as special cases. F sub 0 and f sub 1, we consider this as special cases. F sub 1, the number of rabbits in the first month. The number of rabbits in the first month, we know that it's one pair. There's only one pair of newborn rabbits. The number of rabbits in the 0 month. So on the month before the first month, there are no rabbits. On the month before the first month, there are no rabbits. So there are 0 months there are 0 rabbits on the month before the first month. Let me put everything here. Then the current relation looks like this. F of 0 equal to 0. F sub 1 equal to 1. F sub n equal to f sub n minus 1 plus f sub n minus 2. If n is greater or equal to 2. If n is greater or equal to 2. This sequence is very famous. It has a name. It's called Fibonacci sequence. This sequence is very famous. It has a name called Fibonacci sequence. Fibonacci is the name of a mathematician. This sequence is very famous. It's called Fibonacci sequence. That's part A. Find the recurrent relation. Part B. Find the number of rabbits in the 8th month. Find the number of rabbits in the 8th month. Since f sub n represents the number of rabbits in the island in the nth month, for the number of rabbits in the 8th month, we are looking for f sub a. This is a recurrent relation. We must start calculation from f0, f1 up to until fa. This is a recurrent relation. There's no shortcut. We must compute f sub a step by step. F sub 0 is 0. F sub 1 is 1. F sub 2 is the formula. F sub 1 plus F sub 0, which is also 1. One plus 0 is 1. F sub 3, that's F sub 2 plus F sub 1. 1 plus 1 is 2. F sub 4, F sub 3 plus F sub 2, that's 2 plus 1 equal to 3. F sub 5, that's F sub 4 plus F sub 3, which is 3 plus 2 equal to 5. F sub 6, that's F sub 5 plus F sub 4. 5 plus 3 is A. F sub 7, that's F sub 6 plus F sub 5. That's A plus 5 equal to 13. F sub A, that's F sub 7 plus F sub 6. 13 plus 8 is 21. So there are 21 pairs of rabbits in the island. Here F sub n should be the number of pairs of rabbits, not number of pairs, not number of rabbits. It should be number of pair of rabbits. F sub n should be number of pairs of rabbits. Number of pairs of rabbits. Each pair has 2 rabbits. So, in the 8th month, there are 21 pairs of rabbits in the island. In the 8th month, there are 21 pairs of rabbits in the island. This is a very famous sequence. It's called Fibonacci sequence. And this number, they are called Fibonacci numbers. This sequence is called Fibonacci sequence. And these numbers, they are called Fibonacci numbers.